Welcome everyone. It's a great pleasure that you welcome Andrew Wilson today at New York University.
It's really great to be here. I actually did my PhD at Cambridge, and I started my PhD in this area. There was a machine learning summer school in 2009, sort of on this campus at the Newton Institute in the Center for Mathematical Sciences. And in some sense, the talk I'm going to give now is what I might tell myself if I could go back in time to 2009 and sort of compress a lot of learning that has happened the hard way. With material that I couldn't really find in textbooks, but started to sort of get some intuition about through experience. And in some sense, this is going to be a philosophy for how we can approach model construction towards building autonomous learning agents. And much of this is going to invoke the notion of soft constraints rather than hard constraints and uncertainty representation. This is going to touch on quite a variety of different works I've been involved with, and I've worked with a number of wonderful collaborators on those projects, and this is actually a good chance to give an overview of some of the things that I'm interested in as well. And if there's one or two of these things that you are particularly interested in, say equivariance modeling or Bayesian neural networks or generalization bounds, I'd love to just like chat with you about those things in detail offline or during the talk if there's time. So let's warm up with a question. Let's suppose we have airline passenger numbers indexed by time, recorded monthly, and we're going to consider three different choices that we could use to fit these data points and make predictions up until 1961, a linear function, a cubic polynomial, or a 10,000th order polynomial. Let's just do a poll. Who would go with the linear function? Raise your hand. Who would go with the cubic polynomial? You might hate all of them, but assume you have to choose one of them. Who would go with the 10,000th order polynomial? Okay, so it's actually kind of split. Usually it's about 80% linear function, 10% cubic polynomial, and then maybe a little bit of noise that votes for the 10,000th order polynomial. But I'm going to argue that I would want to go with choice 3. And if I'm unhappy about choice 3, it's actually because it doesn't have enough parameters. It's not sufficiently expressive. The reasoning behind that is, well, the real world is probably going to be quite complicated in many cases, the ground truth solution in this instance. And we're going to have a better chance of modeling that ground truth solution effectively using choice 3, which contains choices 1 and 2 just as special cases. We just have to be thoughtful about how we estimate those AJ parameters. Okay. So we'll return to that in a moment, but first let's consider another question. And there'll be lots of questions in this talk, so don't be shy. Feel free just to speak up, and also feel free just to ask me any questions as you have them. So what makes deep learning different? Does anything come to mind? There are lots of potentially right answers to this.
Training.
Training, the way that they're trained. Or
Over-parameterized model with
more parameters than data points often, yeah.
gradient.
Yeah, so that definitely relates to the last slide. Loads of parameters, and in many cases more parameters than we even have data points.
Not easy to interpret?
Sorry, not easy to interpret, very uninterpretable, yeah. Anything else? Okay, so quite often over-parameterization, having more parameters than there are data points, is associated with neural nets. So that was something that we were reflecting on just a moment ago in that airline passenger number example. Benign overfitting is another phenomenon that's often associated with deep learning. In fact, there was a quite impactful paper at iClear 2016 called Understanding Deep Learning Requires Rethinking Generalization. I think it's been cited like 10,000 or more times. And it showed that convolutional neural nets could fit images with random labels perfectly and achieve zero training error, but of course could also generalize well when they're trained on structured data. And this was presented as in the face of everything we know about generalization and specific to neural nets. Double descent is another phenomenon that is often closely connected with neural nets. That's where, as you increase the flexibility of your model, first your generalization error decreases as you're capturing more structure in the data, then it starts to increase corresponding to overfitting, and then it starts to decrease again. And that second descent is considered quite remarkable. It's where it gets its name, and it's often thought about in connection with neural nets. So in this talk, I'm going to argue with particularly simple examples that none of these behaviors are in fact unique to deep learning, and they can be intuitively understood and rigorously characterized using generalization frameworks that have actually existed for a very, very long time, many decades. And the intuition behind a lot of this argument invokes a notion of what I'm calling soft inductive biases. So quite often we think of generalization in terms of restriction biases. Can you think of an example of a restriction bias? Maybe in the first question I asked you could include an example of that.
Increasing function.
Right? Yeah. So you could say, okay, I know that I want to model data that is strictly increasing, so we'll include that bias. I think that would be a sensible thing to do if you were sure of that. Other examples could be maybe equivariances, like maybe you think your problem is like rotation equivariant or something like this. Maybe you're modeling molecules where that's likely to be the case. Another sort of common thing that we do is we restrict the expressiveness of the hypothesis space. So for example, using the lower order polynomial instead of the higher order polynomial to try to avoid overfitting. But we don't need to do that. We can instead often have extremely flexible hypothesis spaces in combination with just soft preferences for certain solutions over other solutions and achieve very good generalization, quite often better generalization than we would achieve using only restriction biases. And so this is illustrated conceptually here where we start with a restriction bias. Maybe we're ruling out, for example, solutions that aren't rotation invariant. And then we expand the hypothesis space, but we still have a stronger preference for certain solutions represented in darker blue here. So maybe we think that the problem likely has some kind of invariance, or maybe it has some kind of approximate invariance, and so we want to represent that. In the polynomial example, we might want the expressiveness to represent the honest belief that the processes that generate real-world observations are often quite sophisticated, but we also want some sort of Occam's razor property in the way that we fit data. So if we can fit the data using simpler, more compressible solutions, we probably want to encourage our learning procedure to do that. And so one way to do that with a very large polynomial could be to have a regularizer that penalizes the norms of the higher order coefficients much more than the lower order coefficients. So that's different than, say, standard L2 regularization. And so if you do that, you can imagine observing data that basically falls onto a straight line here. And here I've actually, like, this isn't a conceptual figure, it's something that I actually did. So you take a 150th order polynomial, fit the data with it, but have this order dependent regularizer, and it will fit it using a very simple curve compared to what you get if you use an unregularized approach in brown there. And then as you increase the complexity of the data, the model will still be able to perfectly fit that data, but it'll only sort of increase its complexity as needed. So it's not really using extraneous complexity in order to fit the data. So it's kind of like embrace an expressive hypothesis space, but then use the solution that is as simple as possible that's still consistent with what you observe. And that's a principle that will enable generalization in quite a variety of different settings. And as I'll argue a little bit later in the talk, it's a principle that's kind of implicitly encapsulated by newer neural network architectures like very large transformer models. Okay, so another philosophical question. Should we use a different model if we have different size training sets? So let's say I have 5 data points and 5 million data points, both drawn from exactly the same distribution. And I'm considering whether I should use a model of a different size to fit each of these data points. So each of these data sets. So raise your hand if you think I should use a different model.
It depends if you regularize or not.
Mm-hmm. Yeah, it could.
During training or by some penalty.
So assume that you're free to specify the regularization in any way that might be sensible. And let's also assume you don't care about computation. We're just being philosophical. I mean, I think everyone knows what I want you to say. So like, I would not use a different model. I think typically people would assume that we should use a different model because if we use, for example, the 10,000th order polynomial to model a problem with 100 data points, like on that first slide, we might end up overfitting the data, sort of achieving low training error, but producing unreasonable predictions. Perhaps we can avoid that if we regularize in a certain way, et cetera. But the reason that I think that we shouldn't change the model we're using depending on how many data points we happen to have access to is because usually the number of data points we observe wouldn't affect our beliefs about the process that generated those data points. And a good recipe for model construction is just to honestly represent our beliefs into the generative model for the data. And so if I have 5 data points or 500 or 5 million data points, it usually, maybe with some unusual, strange exceptions, would not change my beliefs about what actually generated that data. And so if I'm just honestly representing my beliefs, it's not going to change how I fit the data. There are other reasons that are kind of interesting for why you might want to embrace a very flexible model, even if you have a small number of data points.
Unless you do it adapt. I mean, unless you build your model after you've seen some of the data points. I mean, you enhance your model.
You could do that.
Then you maybe start with a simple one. And then you've seen a bit of data, you enhance the model, you add components, that's what
Right. So the approach I would
active learning, I don't know what it's called in your field, but I mean, you sort of, even if you're given the 5 million at first, you could just say I look only at a few of them, build a model and enhance it.
You could do that. The approach that I would use at a high level typically would be related to that polynomial example. So I probably wouldn't use a polynomial, but I would use a very expressive model that has a strong compression bias. It has a strong simplicity bias. And so if it can fit the data using a solution that can be represented using a small number of bits, then it will do that. And then it will kind of adapt its complexity as needed. So if you just have a few data points, it will use a very simple sort of fit typically. But there's another sort of interesting reason why expressive models can be sensible even when you have a small number of data points. So if I were to play devil's advocate, if I were to argue the other side of this, I'd say, okay, well, even if you believe the real world is a very complicated place, if you just see 2 or 3 data points, your model is not going to be able to extract very sophisticated structure from those data. So you're just wasting a lot of computation and modeling effort in trying to use that kind of model in that setting. But let's actually consider uncertainty. So let's suppose we observe these 3 data points, and we're doing some kind of regression. There are many possible curves that would fit this data. And in some cases, it would be hard to know which one of these necessarily that we would want to use. Maybe in this case, we might be strongly biased towards something that looks close to a linear function, but I could have shifted this point down here, and then maybe we're even more uncertain about which curve is reasonable. And so if we use the sum and product rules of probability to represent all of these solutions and we marginalize over them, then our uncertainty is going to naturally grow as we move away from the data. Whereas if instead I use just a simple linear function to fit the data, even if I'm being probabilistic in the way that I estimate that function, I'm using Bayesian inference, etc., that model will become quickly constrained by the data, but erroneously constrained. And so its uncertainty will kind of not actually reflect our beliefs about what the uncertainty should be. So that's an argument for using a very flexible model, even when you have a small number of data points.
Yes, so here you are not applying a Occam razor, in a way you are going against.
So I guess this latter point is a little bit orthogonal to Occam's. I wouldn't say it's for or against Occam's razor. It's more trying to express the belief that there are going to be many solutions that are consistent with what we observe. And probability says, okay, well, we should represent all of these. So maybe we have some function, f of x equals, some polynomial. And then we put some distribution on the AIs. And once we observe our data, we're going to form this predictive distribution. And maybe we have sort of some observation model. And then we just sort of marginalize over the posterior. And so this is just sort of a direct consequence of the sum and product rules of probability. And so if we're following this kind of estimation procedure, if we use a model that doesn't really represent our beliefs, that the process that generated these data points actually probably is quite sophisticated, then our uncertainty will just become kind of erroneously constrained and our model will be overconfident, even though those data points might not provide a lot of signal to extract a very detailed sort of representation for the data. Does anyone disagree with that? Does anyone think we should still use the linear function?
I think
when we have small amounts of data, don't we need strong assumptions in place to make progress on it?
Otherwise, you'll get really
Otherwise,
wild
you get, yeah,
and then there wouldn't
you
be.
know
I mean,
nothing.
I'm not saying the linear
Yeah.
be used, but then exactly, yeah.
So I'm not saying we shouldn't make assumptions. We have to make assumptions. And I think
Yeah.
this is sort of, I mean, regardless of how many data points we have. And I think this is sometimes a point that's a bit lost in modern machine learning. So our assumptions aren't as transparently represented by modern neural network architectures. But of course, they have to be making assumptions because machine learning is learning by example. It's inductive learning. And so in order to do that, you have to make assumptions. And then there's this question of, well, how should you represent those assumptions and how universal might those assumptions be? And that's something I'm going to get to a bit later in the talk. But I'm not against assumptions. I am generally against restriction biases unless we're absolutely confident that we want to include certain types of solutions. And I think typically we're not. And so in the polynomial example, we typically wouldn't be confident, okay, it could not be more than like a third order polynomial or something like that. Maybe we think that the coefficients of the higher order terms should have very low variances because we only want to use them if there's a strong signal in the data saying we should use them. But yeah, assumptions are good, but I don't really like restriction biases. So I think a Gaussian process is a good example of something that combines both, and I'll talk about that a little bit later. So Gaussian, yeah, actually I'll save that for this slide. Okay.
So
Yeah.
in some sense, I mean, this is a Gaussian process that you're now
It is.
using as a model. And in some sense, what you're saying is related to the kernel and to the feature space, right?
Yeah.
So you're basically saying, if you use the Gaussian process, think twice before using a finite rank model. And maybe if you go to the limiting argument in your reasoning, use a kernel in the first place that has a richer feature space. Is this what you're doing?
Yes, this is something I believe. So I've done a fair bit of work on scalable Gaussian processes, and a lot of the early work, not my work in this space, involved low rank representations of the kernel matrix. And I didn't really like those because it felt like we're sort of throwing away what we loved about Gaussian processes in the first place, which was this sort of magical representation that enabled us to have almost arbitrary flexibility combined with some sort of Occam's razor bias that would be represented by our choice of covariance function. And so as a consequence, a lot of my work on scalable inference has been trying to avoid those types of approximations. So either understanding the structure that might arise in the covariance matrices from the kernel functions that we're using in the first place. Like if we have like a product kernel on a multidimensional lattice, then the covariance matrix will sort of decompose as a Kronecker product. Or if it's a stationary kernel on a one-dimensional problem, then you'll usually get toplet structure. And then you can basically solve these linear systems and do these other matrix operations a lot more efficiently, but get the same answers as if you were using the naive and cubed algorithms. And so in some sense, it's just like we were paying too much for lunch and it's not a free lunch and we should pay the right amount. And I think this is actually a principle that applies quite generally. Quite often our modeling assumptions will manifest as some sort of algebraic structure that we can then exploit algorithmically for computational efficiency. Another sort of approach that I've really advocated for is just parallelizing on hardware. So instead of using procedures like Cholesky decompositions, which are recursive and hard to parallelize, use linear conjugate gradients if you want to solve a linear system. And this just involves iterations with a bunch of matrix multiplications, and this can be parallelized very effectively on a GPU. And so those types of iterative methods, including things like stochastic Lanczos quadrature, if you want to compute log determinants or other types of matrix operations, are the backbone of GPyTorch, this library. And we managed to scale GPs up to millions of data points just using these iterative methods combined with reasonable preconditioners and basic consumer grade GPUs. And so this is usually the approach I advocate for, and this is partly why.
Maybe to carry on the philosophical aspects. I mean, like I talk about Occam's razor, but it's also the minimum description line where you say that you try to minimize both the size of data and the number of parameters. And I got work of Al Dewey, and we show that neural networks are so well because of the simplicity bias, so by minimizing the common complexity of the neural net. So
I'm getting, yeah.
That's it?
I'm getting to that in a bit too. Yeah, okay. Okay.
Yeah.
But did you have a different? Well, okay. Well, let me know if you still have a question.
I see what, like when you, for me, when you say should we use a different model for different training data sizes, I would say yes. So if you have less data points, then you have to simplify your model to be able to generalize because of the MDL principle, but you won't still minimize the descriptors there. And so, which is like the side of data plus number of parameters. And in order to be able to generalize, you have to make it as simple as possible, combining both number of parameters in the model and the set of data set.
But there doesn't have to be a tension between the expressiveness of the model and its simplicity bias. So if we consider something like Solomonov induction, which actually formalizes an ideal learning system, it's a maximally over-parameterized model representing every possible program, but it has exponentially higher weights for solutions with lower Kolmogorov complexity. And so I think this is how you can kind of resolve these two things.
Yeah, okay.
Yeah. Okay, so if we go ahead and just use that sort of toy polynomial on a bunch of different problems with varying training set sizes, we do often see that we get kind of the best of both worlds. So in the left panel here, we have data which are generated from a second order polynomial. We fit it using a 15th order polynomial that's unregularized and a 15th order polynomial in green that has order dependent regularization. We see in this case the order-dependent, higher regularized, higher order polynomial behaves quite similarly to the perfectly specified model, whereas of course the 15th order polynomial that's unregularized is not getting very good generalization error. In the middle panel, we have data generated by the 15th order polynomial. Interestingly, the 15th order polynomial with the order-dependent regularization is much better than the unregularized one and also better than the second order polynomial. In the third panel, we have data generated by a function that's out of class for all of these models. And again, the 15th order polynomial with the order-dependent regularization provides the best generalization for all numbers of training points. And so essentially, when you have a small number of data points, this model might behave a little bit like the second order polynomial because it has a very strong simplicity bias. As you increase the number of data points, the model is adapting its complexity as needed and achieving better generalization. Okay, so another example I briefly mentioned of a restriction bias are symmetry constraints. So things like translation or rotation equivariance. And a very famous example of that would be convolutional layers. So they have approximate translation equivariance. And you can derive a convolutional layer by starting with a fully connected layer, removing a bunch of parameters, and then enforcing parameter sharing. So all the lines in here, in purple here, share the same value, and green share the same value. But we can relax this constraint in the spirit of soft inductive biases by instead going back to the densely connected linear layer and then penalizing the norms of any parameters that don't exist in the convolutional layer, as well as the distances between any parameters that would otherwise be shared in the convolutional layer. And then the values of these coefficients will determine how much like a convolutional layer we want this to behave. There are more elegant ways of trying to do this, and so we have a set of papers introducing what we call residual pathway priors. So in this example, you can put a distribution over the neural net parameters that has a covariance matrix that lives in this equivariant subspace Q, plus some orthogonal complement that sort of relaxes that constraint. And what we found, interestingly, is that we needed only a very small bias for the symmetry constraint in order to achieve as good performance as perfectly constrained models. And then in cases where the constraint in the data was actually approximate, of course, this procedure would work a lot better than a model that was perfectly constrained and a model that had no constraint bias at all. And so that was a little bit surprising to me. With hindsight, it's maybe not as surprising because if you have a very flexible model and it has to pay any penalty, no matter how small, for deviating from a particular type of structure, and that structure perfectly describes the data, you can achieve zero training error using that structure, then the model will basically just collapse onto that structure and you'll end up with like the perfectly constrained model, even if you have a very small number of data points. More generally, the idea behind residual pathway priors is you have your inputs that are kind of mapped to a restrictive layer and a more flexible layer, and you try to fit basically as much as possible with the restrictive layer, and then you kind of fit the residual with the more flexible layer. And this is another conceptual illustration of how training might proceed with soft inductive biases. So in the left panel, we have a flexible model combined with a uniform bias for different types of solutions. And so in this case, we might often indeed see overfitting. In the middle panel, we have an equally expressive hypothesis space, but we have stronger preferences for certain solutions over others. In this case, the model can actually be guided towards solutions that both have low training loss and encapsulate sort of reasonable structure that we might expect to describe the problem approximately. In the third panel, we have a restriction bias, which constrains the size of the solution space that we're representing, but as a consequence, it often prevents us from finding more optimal points of generalization. Okay, so this so far has been mostly intuition, but this intuition can be quite rigorously characterized using generalization frameworks that have existed for a very long time. So these include Pack-Bayes. They also include simpler accountable hypothesis bounds with a prior, and so we'll start with those. So this is one of the simplest such bounds where we have the expected risk is upper bounded by our empirical risk, our training loss, plus a complexity penalty term. And we'll sort of parse everything in this expression. So in this complexity penalty term, we have a delta, which corresponds to the confidence of the bound. So as delta gets stronger or lower, this is sort of a stronger probabilistic statement, and so our bound is going to get looser. N, which corresponds to the number of training data points that we use to evaluate the empirical risk, and this pH, this prior over hypotheses. Now, something that's very important to understand about this prior is it does not have to be well specified. It does not have to be used by the model. It's just something we use to evaluate the bound. It's like a prior weighting function over different solutions. And I think frameworks like Pack-Bayes have a lot of surface level name recognition, but not many people have internalized this point. I think there's a lot of confusion about, well, how do you choose the prior, and like, does it have to be used by the model, or can it be used to generate the hypothesis for the problem you're modeling? It doesn't matter. It can be whatever you want. If it's a bad description of how the model behaves, then your bound will simply be loose. I found that a very useful prior for evaluating these bounds is called the universal prior, or the Solomonov prior, which says that the prior over hypotheses is equal to 2 to the negative Kolmogorov complexity divided by a normalizing constant, which by the Kraft inequality is going to be less than or equal to 1. And this allows us to sort of substitute this prior into this bound to get the expression in equation 2, where now basically we're saying that if we have a model that can achieve low empirical risk, so it can fit the training data well, and it's finding a solution that is very compressible, that can be represented using a small number of bits, then we're guaranteed good generalization. And relating to the point I mentioned about priors, this bound is applying to the models that we're actually using in practice. So deterministically trained models, these models don't have to be Bayesian, they don't have to use some sort of explicit prior distribution, etc. So the recipe for evaluating these bounds is just to train your model to find some solutions, so some setting of parameters that fits the data, evaluate the training loss, evaluate an upper bound to Kolmogorov complexity, which is the compressed file size of your trained model. And then you just plug everything into the bound and evaluate the number that you get. And then from this bound arises a prescription, which is essentially what I've already been saying. Embrace flexibility so long as it's combined with some sort of simplicity bias that can be formalized in terms of Kolmogorov complexity, which is the shortest program that can generate a hypothesis. Of course, we don't know what the shortest program is, but we can easily upper bound it. Mm-hmm.
So everything in this framework is related to the empirical risk, which is just looking at pointwise predictor. So you're not interested here in probabilistic properties of your predictor.
Not yet, yeah.
Right. Okay.
Yeah, I'll get to that in a moment, yeah. Mm-hmm.
Just one group, I would like to comment about the structural risk minimization of that page.
Mm-hmm.
So for me,
Mm-hmm.
it looks a bit the same.
It's
so,
related, yeah.
Yeah.
Yeah, I mean, it's certainly an example of
Yeah.
how you can encode a soft inductive bias. I think partly there's maybe a difference in, like a sort of a soft difference in perspective.
Yeah.
in that often structural risk minimization is used to reduce things like VC dimension, et cetera, whereas I'm saying, actually, we don't care what the VC dimension is. It can be anything, but it's a way to encode a soft bias. There are many other ways, though, that we'll get to, like over-parameterization, interestingly, is another way to encode sort of a soft bias for simplicity, which is perhaps a bit counterintuitive. And then there's this framework, and I guess, so this is related to two papers. One I've listed on the slide, where we're talking about universal learning, and another more recent one called Deep Learning is Not So Mysterious or Different. And in the latter paper, I'm really trying to make the point that actually a lot of these ideas, at least at a high level, are not new. They're relatively old. And for some reason, they just have not been internalized by the machine learning community, especially the deep learning community. So there was this paper, Understanding Deep Learning Requires Rethinking Generalization. And they say very clearly in the paper that there's sort of no existing sort of rigorous framework that is sort of kind of, it describes this behavior in the sense that you can sort of evaluate a bound when a model is trained on noisy data and fits it perfectly and it's loose, and then evaluate the same bound when it's trained on structured data and it's sort of reasonably descriptive of the model's generalization. And so if you use these sorts of frameworks combined with the Solomonov prior, then you can get very tight descriptions. Interestingly, though, I don't think that the form of this bound is also very widely known. So it's sort of been around in some sense for a while, but this is more related to something called the finite hypothesis bound, where you basically have a uniform prior over hypotheses. So by actually including sort of an explicit non-uniform prior over hypothesis, this bound becomes much more powerful. And I don't think there's necessarily much broad awareness of the form of this bound, even though it has existed in various ways for a while. It can be found in the Shayla Schwartz and Ben David book on learning theory. Okay. So we can visualize basically how these two terms influence our upper bound. So if we can use a model that is expressive enough to fit the data well, but still provides a good compression, then we'll get a good bound. And interestingly, and this is something I'll get into in a bit, we find that the larger we make our models, including billion parameter LLMs, the tighter the bound becomes, and the better these models often are at actually compressing their solutions. So there was a question about probabilistic models. So PAC-Bayes basically replaces this log 1 over pH term with a KL divergence between some distribution over desirable solutions Q and your prior P. Q doesn't have to be the Bayes posterior, but it can be. I think this is also a point that maybe isn't broadly appreciated. So there was sort of a line in, so they had sort of like a follow-up to this rethinking generalization paper called Understanding Deep Learning Still Requires Rethinking Generalization. And they have sort of a brief reference to PAC-Bayes, but it just says, in cases where the model is allowed to output a distribution over parameters, new generalization bounds have been derived. But even PAC-Bayes can apply to deterministically trained models. Like you can have a point mass posterior and get a valid bound. And in fact, if you just sort of write out the definition of KL divergence as relative entropy, and then you have Q being kind of a Dirac delta function, you'll get a log 1 over pH basically back. And then you need to have like a countable hypothesis space, but that's all right, because every program on a computer in floating point arithmetic is a finite program. And so these bounds do apply to those models. Okay. There's also something called the marginal likelihood, which is very directly connected to PAC-Bayes bounds. They're kind of interchangeable, and this will become important in a moment. Okay, so let's now consider the Bayesian perspective. I've been talking about soft inductive biases and generalization frameworks that apply quite broadly, but I think we can get some additional insight by thinking about model construction through a Bayesian lens as well. So from this perspective, we want to have distributions over solutions in our prior, and then we observe some data, and then we infer some posterior distribution over solutions. So if we go back to that first choice on that first slide, the linear function, and we put a distribution over the parameters, W0 and W1, this will induce a distribution over straight lines with different slopes and intercepts. And from this perspective, we can imagine a conceptualization where we have all possible data sets that we can generate from our model on the horizontal axis, and the probability of generating those data sets from our prior over solutions on the vertical axis. And that is exactly the marginal likelihood. So the marginal likelihood is equal to so it's basically the probability that we would generate our data set from our prior. And so if we have like a simple linear function, we're not going to be able to generate very many different data sets, but those data sets are going to have a lot of probability mass under our model. If we have like a really flexible model with very generic inductive biases, it might spread its mass very thinly over all sorts of different data sets. So I don't think that's really a good thing. You can also kind of get the best of both worlds by having a very expressive model, but it still has fairly strong preferences for certain types of solutions over others. And that's represented by this green curve here, and that could correspond to a model like a convolutional neural net that does have certain types of inductive biases. So,
the question is, so you said that you are passing from two different frameworks, but the previous one can be also viewed as sort of the induction can be also viewed as Bayesian from Bayesian perspective.
yeah.
Yeah. Okay.
Yeah, yeah.
So in a way, they are related.
Oh, they're very related. So I think the Bayesian framework is just a very nice way to exemplify some of these principles. It's not the only way, but it's a way that I like, basically. Yeah.
Additional version of it.
It's a way to sort of put these principles into practice. There are other ways. You can do regularization. You can sort of have implicit biases from your optimizer, et cetera. But this is more like the Bayesian perspective, and it's very much connected to what we were discussing earlier. Yeah. Okay, so in these three panels, basically we see what happens is each of these three models are exposed to a particular data set. So the green model has an expressive hypothesis space. It casts a wide net. So there's some setting of its parameters that will be a good description of ground truth reality. And it's able to fairly efficiently contract around that good solution because it has reasonable inductive biases. The blue model is quickly constrained by the data, but it's erroneously constrained. It can't represent anything that's very close to the ground truth solution. The red model is flexible, but because it has very weak generic inductive biases, it doesn't learn very efficiently, and so it doesn't help you find a very good solution. Okay, so what's different about Bayesian approaches versus the alternatives? Many people would say the prior. I think that's usually what comes to mind. And then there are all sorts of questions about that, like how do you know your prior is well specified and stuff. And we could talk about that a lot. I would just say that all of those criticisms are both valid and applicable to virtually any non-Bayesian framework as well. Like how do you specify your model? How do you specify your likelihood? Like you have to make assumptions and you have to be willing to defend those assumptions. And not using a prior is also kind of an assumption. And probably not a very easily defensible one in many cases. So I think the distinguishing property instead is really this thing called marginalization. So rather than bet everything on a single solution, consider all solutions that are consistent with your observations and then weight them by their posterior probabilities. And so if we look at this figure here, we see that there are many curves that are consistent with our data points. And probability theory tells us, let's not just use one of them, let's use all of them and then just weight them using this Bayesian model average. And then when we do this, we'll have uncertainty which kind of intuitively grows as we move away from the data. And then that's going to be very useful in active learning settings where we need to sort of decide where we might see a lot of value in measuring additional data and decision making, of course. And it's also just like representing our honest beliefs. And so more specifically, when we make predictions using a Bayesian framework, we marginalize all possible solutions weighted by their posterior. So equation 6 here, y are our labels, our outputs, x are our inputs, w are our parameters. It's saying, well, let's not just use one setting of parameters, let's use all settings of parameters weighted by their posterior probabilities. This reverts to the classical optimization framework when our posterior is very concentrated around a particular set of solutions. And so you can kind of view just standard training as some sort of approximate inference where you represent your posterior as a point mass centered around the setting of parameters that maximizes the posterior. And so that will be a good approximation in cases where your model is very well determined by the data. But it will be a very bad approximation when your model is often very expressive and there are many settings of your parameters that will be consistent with what you observe. And so that is particularly the case in deep learning. These models are extraordinarily flexible. And so this is really an argument, perhaps contrary to some conventional wisdom, that Bayesian methods might have the most value in deep learning rather than the least value in deep learning, because that's where we stand to gain the most by doing marginalization. Of course, computing this integral is going to be very challenging. It's very high dimensional. The posterior is very multimodal, etc. But I think we should at least try, because this is just trying our best to represent our beliefs under whatever constraints we might have, computational or whatever else. And we just don't believe in many cases, especially if we're using a big neural net, that our parameters are going to be completely determined by the data. Okay, so now let's use some of these principles to try to understand some of these generalization phenomena that I've mentioned. So the first of these is benign overfitting, and so we've already talked about this a little bit. Can we do benign overfitting with that basic polynomial that has that order-dependent regularizer? The answer is yes. So we already saw that this model can adapt its complexity as the data gets more sophisticated. It can also perfectly fit uncorrelated noise in panel C here. And so this simple polynomial model can do benign overfitting just in the same way that a convolutional neural net can do benign overfitting. And so if understanding generalization requires rethinking deep learning, it also requires that this polynomial's behavior sort of also should make us sort of need to rethink generalization. We can also exactly reproduce the results in that paper using Gaussian processes. And so in the top row here, in panel A, we have sample prior functions from a Gaussian process with a standard RBF covariance function. In panel B, we look at the posterior predictive distribution of that Gaussian process when we expose it to some structured data, so it looks fairly reasonable. In panel C, we give it a bunch of corrupted labels, and we can see that the posterior predictive can also perfectly run through all of those data points. So this is an example of a model that has a very expressive hypothesis space, but it really wants to avoid using certain types of solutions if it can. And this is something we can actually precisely quantify how much the model wants to fit certain data using the marginal likelihood. What's the probability of generating that data under the prior over solutions? And so if we went back to panel A and we kept sampling those prior functions, we would have to sit there sampling for a very long time to see anything like this red curve, because it has very low probability density under this prior. But it's there. So if we sat there for like a couple million years, eventually we would get this red curve. But if you tell the model, okay, well, you have to fit the data, it can say, oh, well, I am flexible enough to do this. And so that's what we'll get. We can also apply Gaussian processes to that image classification task, CFAR10, with like varying numbers of altered labels. And we can see that it can fit the training data perfectly in each case and still provide reasonable generalization, just like a convolutional neural network. And we can compute the marginal likelihood of the Gaussian process. And we can show in teal here that it goes down as we increase the number of altered labels. So indeed, the Gaussian process prior is saying, well, I can generate this data, but it's having increasingly low kind of probability density under my prior. We can do exactly the same thing with the neural network. And as I said, the marginal likelihood actually directly corresponds to these packed base bounds. So these bounds are getting looser as we increase the number of altered labels. Overparameterization. Okay, so this is probably starting to feel quite natural, this idea that it might be okay to have more parameters than there are data points, as long as we have reasonable kind of soft biases for certain types of solutions over others. And Gaussian processes, I think, are really a perfect example of this philosophy. In fact, work on Gaussian processes in the machine learning community was triggered by work on neural nets in the mid-90s. So Radford Neal was a big proponent of this philosophy that we should build as big a model as we can kind of fit in memory, because this is an honest representation of our beliefs. And in his PhD thesis, he had some nice examples, like if you're doing character recognition and you have a simple model that works well, you always can build a more complicated model around that that has whatever properties cause the simple model to work well, that works even better by accounting for, say, irregular ink blots or strange writing styles or whatever else it might be. And accordingly, he was interested in pursuing the limits of Bayesian neural nets. So what happens if you have an infinite number of hidden units, for example, in a Bayesian neural net. And using a central limit theorem argument, he showed that those infinite neural nets would actually converge to Gaussian processes with particular covariance functions. And many of the standard covariance functions that we use, like the RBF kernel, can also kind of be derived in a similar way. Like the RBF kernel is sort of an infinite number of densely dispersed radial basis functions in the weight space view. And so these models are actually more flexible than any neural net that we can fit in memory, but we find they often achieve their best generalization relative to other model classes when we have somewhat small data sets. And so I think this is actually a kind of a very nice demonstration of these principles. As I mentioned earlier, Solomonov induction is also kind of an example of this principle. So it's sort of a formalization of an ideal learning system, and it represents like a maximally over-parameterized model with the ability to represent any program that can be stored on a computer, but it has kind of exponentially higher weights for solutions that have lower Kolmogorov complexity, shorter programs. Okay, so why does over-parameterization in deep learning tend to lead to simpler, more compressible solutions? So this is something we'll verify in a moment, but I'm just going to give a little bit of intuition for this. And I'll caveat by saying this is, of course, very hand-wavy intuition, but it's something that we can characterize more rigorously later. So as you increase the number of parameters in a neural net, typically you increase the relative volume of the flat solutions in the objective function that you use to train the neural net. And by flat solution, I mean that you can perturb the parameters that you have found and still get fairly low loss. So imagine you have two regions in this optimization objective that are flat, meaning that the loss doesn't vary much in those regions and it's low, with radiuses, say, RA and RB, and RA is greater than RB. As you increase the number of parameters in your model, RA to the D starts to dominate RB to the D. And so there are many, many more kind of solutions that can be described as flat. And so that means that as you continue to increase the number of parameters in your model, you increase the relative volume of solutions that will fit the data well, but are also fairly compressible and will provide better generalization. Because if you have a flat solution, kind of by definition, you don't need to represent it with as much precision. And so it's going to be much more compressible. And in order to do that, it's going to be needing to discover certain irregularities in the data, like invariances or whatever else that enable kind of compression that will also likely enable better generalization. And so empirically, this seems to be very much the case. So there's a sequence of works, not from my group actually, from Tom Goldstein's group at the University of Maryland, where he's arguing against the idea that the implicit biases of stochastic optimizers play an important role in deep learning generalization. So I think for a long time that was the conventional wisdom. It might still be even that like we have these terrible non-convex objective functions to optimize, and it's kind of crazy that neural net like we learn anything reasonable that makes good predictions. But possibly the reason for this is we're using SGD or some other stochastic optimization procedure that causes our training to sort of navigate some subspace of solutions that will achieve better generalization. It might have a bias towards flat solutions, etc. So in one paper, they showed that you could actually just do full batch gradient descent and achieve similarly good solutions as if you were using SGD. Of course, it's not very computationally practical. In another paper, they took this a step further and they just did guess and check. They just like randomly sampled their parameters from like a very generic kind of uniform prior and then stopped as soon as the loss was below a certain threshold. And they found that those solutions were comparably good to what you would find if you were using SGD, Atom, etc. And so that kind of corresponds to this illustration where if you're just sort of throwing darts at the optimization landscape, you're much more likely to land in an area that has low loss and good generalization versus low loss and bad generalization. Okay, so we can use this to try to understand also phenomena like double descent. So I mentioned double descent is this phenomenon where as you increase the model flexibility, your generalization error shown in solid red here first decreases as you capture more structure, then it starts to increase as you're overfitting in that sort of pink region, and then it starts to decrease again to often a value lower than it was in that sort of first classical regime. We can sort of relate posterior contraction in Bayesian neural nets to a quantity called the effective dimension of the Hessian, which basically counts the number of relatively large eigenvalues in the Hessian evaluated at the parameter vector that you get after training. If you compute this quantity in the second descent, the effective dimension just keeps decreasing. So in that regime, all of the models have basically zero train loss. So that second descent usually starts at the point that you're perfectly fitting the training data. And so it could not be that the models with larger width in this case are getting better generalization because they're more flexible, because all of those models are fitting the training data perfectly. It has to be something else that you're getting by increasing the size of the model, like a simplicity bias. And so that's something that we can measure with tools like effective dimensionality. And so that goes down. Effective dimensionality goes up in the first regime because the model, of course, is capturing more information. And so its parameters are containing more and more structure. And it's sort of, even in the sort of overfitting regime, it's sort of capturing structure, but some of that structure is noise. It's kind of, yeah.
Maybe just to understand this part of your talk, what do you refer to when you talk about Bayesian neural nets? Because the only ones I've seen that practically are used and work have no dependencies between weight parameters. I mean, between the no correlation between the parameters. So are you having correlation within layer or also across layer, or have you got independent priors on these or distributions on these weights?
So the plot I'm showing here is not using a Bayesian neural net. Posterior contraction of Bayesian neural nets can be used to motivate this quantity effective dimensionality, but I'm just evaluating the effective dimensionality for deterministically trained models. I will actually in a moment show Bayesian neural nets. You can also replicate this behavior exactly with linear models, just like we could replicate benign overfitting with a polynomial. I won't go into the explanation too much, but it's something that we can also understand in the linear model case. Here is double descent with Bayesian neural nets. Here what we did is we had a Gaussian approximate posterior over parameters in SWAG and a mixture of Gaussians approximate posterior in multi-SWAG, and then we do approximate Bayesian marginalization through like simple Monte Carlo integration. We see that with the unimodal Gaussian posterior, there's a little bit of double descent, but it's much less pronounced than with SGD training in orange. With the mixture of Gaussians, approximate posterior, there's actually no trace of double descent at all. And so this comes as a consequence of really trying to combine all the different solutions that the model is representing. This sort of decreases the variance, I guess, from like a classical frequentist perspective in the bias variance decomposition, and basically eliminates double descent. And so you see monotonic improvements in performance with increases in flexibility if you're doing somewhat exhaustive Bayesian model averaging. It's also worth noting here, incidentally, that the test error is a lot lower for the Bayesian procedure than for the standard procedure. So I think there are a lot of misconceptions about Bayesian neural nets, and perhaps one of them is they don't work as well or they work about the same as classical training, but they're more expensive. That's actually not true. So that might have been true initially when people were revisiting Bayesian deep learning around 2015, but there were a number of approximate inference procedures that were developed that actually became very practical. And so this procedure not only gives you better calibration of the model and sort of uncertainty representation that you can use to do things like Bayesian optimization and active learning, it also gives you better point predictions. And that makes a lot of sense. Like if you have a model with all sorts of different weights that provide complementary but compelling explanations of your problem, if you combine them together, you ought to make better predictions.
Could I ask that what's the approximation procedure? Is it one of the standard or is you developed it?
It was something we developed.
Right.
So it might take a while to explain,
Sorry,
but it's okay. It's all right. No, it's a great question. Let me see if I can try to explain it briefly. So we developed an optimization procedure which basically decays the learning rate to a constant learning rate and then takes an equal average of the iterates with this kind of relatively high constant learning rate, and then uses that solution. So it kind of has this running average of like the parameters that you're traversing with SGD or Atom or whatever else. SWAG just does like a kind of approximates the second moment as well. So you get like the empirical covariance of these points that you're sampling essentially by using SGD with a constant learning rate schedule. And then you can form your sort of empirical covariance matrix from that, plus some diagonal term. And that gives you your kind of approximate, Gaussian approximate posterior distribution. And then you can kind of run multiple chains of this, and then you get your mixture of Gaussians, and that's called multi-swag. And so it's probably one of the most kind of practical approximate Bayesian inference procedures for neural nets. Okay. I'm probably way over time. Oh, actually not as bad as I thought. So very briefly, what actually makes deep learning different? So we talked about things that people think makes deep learning different, but might actually not distinguish deep learning. So over-parameterization, no, we see that with Gaussian processes. We can easily get reasonable behavior using large over-parameterized polynomials, etc. Benign overfitting, no. All we need is an expressive model that has a simplicity bias. Double descent, no. We can reproduce that using linear models as well, and we can understand all of these things intuitively, and we can rigorously characterize them using generalization frameworks that have actually existed for a long time. So what is actually different about neural nets? Something has to be different because people are using these models a lot and they work pretty well empirically. Representation learning is not something that's unique to neural nets, but it is something that I think distinguishes them. So typically we can express many model classes as some inner product of parameters we want to learn with some vector of nonlinear basis functions. So polynomials could be an example of that, but the basis functions themselves are basically fixed. This was, I think, historically often thought to be sufficient because you can get arbitrarily expressive models using this procedure. And so, why do something else? But if you actually learn the basis functions, which is basically what you're doing with a particular recipe of kind of matrix multiplications passed through pointwise nonlinearities in a neural net, you can actually solve interesting extrapolation problems and effectively learn some sort of distance measure. So I guess from the kernel or Gaussian process perspective, you can view the model as specifying sort of a distance measure between different data points. And if you're using an RBF kernel, you're basically saying that covariances decrease as a function of kind of squared Euclidean distance between these different points. But maybe that's not always going to be appropriate. Like if you want to, for example, predict the orientation angle of a face, you might want a very kind of non-Euclidean distance measure. And neural nets are very good at learning these kinds of things. So here we have specifically that problem, and we have the representation of the neural net projected into a two-dimensional space where each face is a line segment, and the slope of the line segment is the orientation angle. And so we see it kind of clusters faces with similar orientation angles together. And then you could do something like apply Euclidean distance in that space and get something reasonable. Mode connectivity is another thing. So this was something we discovered when I got interested in working on Bayesian neural nets. As a first step towards doing effective marginalization, we needed to understand the geometric properties of these loss landscapes better. And so historically, it was believed that these optimization objectives would lead you to isolated solutions. So if you retrain your neural net, for example, with different initializations, you'll find different local optima that are isolated in the sense that if you move away in any direction from these local optima, you incur very high loss. And so that corresponds to this top panel here. In the bottom two panels, we found that there are actually subspaces in these optimization objectives where you can walk from any of these solutions to any other solution without increasing the loss along the way. And so this is called mode connectivity. And this is not due to degeneracies in the parameterization of the model. The different parameters along these curves actually give rise to functions which make different predictions on the test data. And so they can be ensemble, for example, even though, of course, they make the same predictions on the training data. And so this just makes things a little bit more concrete. This is how you might parameterize these curves. So if you have a polygonal chain with a single turn here, you get from one solution W hat to the other solution W2 hat by varying t from 0 to 1. Your goal is to learn theta. You can learn theta by minimizing your loss uniformly expectation over the curve. And so you can develop a sampling procedure that will allow you to do that. Okay, the last thing that I think is relatively distinctive about neural nets is their universality. So they're obviously not completely universal, but they're much more universally applicable than we ever expected them to be. And so unlike many other model classes, we use neural nets to solve quite a wide variety of different types of problems, often quite successfully. And so there's this question of how is that possible in light of results like the no free lunch theorems. And so the most famous no free lunch theorem says that every model is equally good in expectation over all possible data sets. And this has historically often been used to argue that the recipe for good generalization on the problem you care about is to try to understand as much as you possibly can about that problem, talk with domain experts, et cetera, encode everything you can into the model and tailor your approach very specifically to that problem, because the no free lunch theorem says that if your model is doing really well on one problem, it has to be doing badly on other problems for everything to average out. But of course, that's not really what we've seen happen in practice. In fact, we've seen the opposite. We've seen a confluence of more specialized learners towards more general purpose models. So feature engineering, SIFT, HOG, et cetera, to neural nets that are modality specific, like convolutional neural nets for images, recurrent neural nets for sequences, MLPs for regression, RL, tabular data, et cetera, to kind of transformers for everything. And so how is that actually possible? Now, part of the intuition is that the real world is a small corner of all possible data sets. The problems that we're modeling are not uniformly sampled from a distribution over all possible data sets. And in fact, most of those data sets that we would sample from that distribution would just be noise. They wouldn't have much structure. Secondly, these different problems share structure, perhaps to a surprisingly large extent. But there's this question about, like, at what level is this structure really shared? And I think there are differing views on this. So there's one view, which I think is called the Platonic representation hypothesis, and that's that, like, all the problems that we're modeling are just projections of some kind of underlying reality. So like an image can be described with pixels or with text, and so if you train different neural nets on those respective modalities, you'll discover similar representations. I don't believe that. I don't think that's really true in general. I think often different problems have very different low-level features. Like you might be modeling molecules, which are rotation invariant, or images, which might be translation invariant, and you would often use very different sorts of features to try to capture that structure. However, what many of these problems have in common is that they're compressible. And so, for example, those different symmetries are different ways to compress the data. And so it could be that the real world data generating distribution has a bias for low Kolmogorov complexity, and so do the models that we're building. And so we can, of course, formalize this in these generalization bounds. We've explored this idea in a paper about no free lunch theorems and had several conclusions. Perhaps one of the most surprising of these conclusions was that convolutional neural nets, which are clearly a domain-specific model that have inductive biases that were intended for images like locality and translation equivariance, provably have biases for even things like tabular data. If you sort of reshape tabular data into an image, you can show that that data has reasonable marginal likelihood, and you can get provable kind of cross-domain generalization bounds. We also found that larger transformers tended to have much stronger simplicity biases. And so this was true of both pre-trained models and even randomly initialized models. This is something that we put into practice somewhat. So we had a paper where we took a transformer which was just pre-trained on next word prediction. So just off the shelf GPT-3 or Llama 2 or whatever else. Didn't update it at all, naively represented numbers as string tokens, and just tried to see what would happen if we had these models kind of extrapolate the next sequence of string tokens. And quite surprisingly to us, we found that this often worked as well or better than purpose-built time series models that had been specifically trained on that time series data we were trying to forecast. So this was completely in a zero-shot setting, so without updating the model at all, which is actually pretty crazy. Like we're not even representing these numbers as numbers. They're just like string tokens. And like you might be wondering about things like data leakage and so on, but we actually did try to control for this. And so we looked also at time series that were sort of demonstrably outside of the training window of the model, and it would provide similarly good predictions. We also thought about uncertainty representation in these models in the way that you do tokenization. So for example, rather than tokenizing each number as a whole, you can tokenize individual digits within the numbers and get this kind of hierarchical softmax predictive distribution for numbers. And so this is kind of interestingly related to sometimes what people do when they treat a regression problem as like a categorical prediction problem. This has always really annoyed me. It seems like the wrong thing to do, like kind of treating regression like classification, where you just have a bunch of bins and you use like a softmax likelihood. But sometimes people find that this works well, and usually when it works well is when your predictive distribution ought to be fairly multimodal or something that isn't naturally very described by standard likelihoods. And so you could try mixtures of Gaussians and things like this, but that can be sort of hard to estimate. So this actually provided a very flexible sort of predictive distribution, which also meant that it did very well on sort of probabilistic measures of performance as well. We've also looked at this for materials generation. So we represented atomistic data as text, the locations of atoms and energy levels and so on, and then just took like a pre-trained next word predictor, fine-tuned it on this data and had it generate inorganic crystals, and it got state-of-the-art performance, to the shock of actually the chemists that we were collaborating with. And we found that the text pre-training was an indispensable component of this pipeline. And I mentioned this a couple months ago in a talk, and someone came up to me afterwards and said, "We read your paper, and we found out how to get rid of the fine tuning. It's just pre-training now on text, and it does just as well." And so that was pretty amazing. All right, yeah. So in short, I think neural nets and a lot of the developments that we've been seeing in deep learning recently are not as mysterious as they're often made out to be, and not many of the phenomena associated with them are not specific actually to neural nets either. A lot of this behavior can be understood through the lens of soft inductive biases and rigorously characterized using generalization frameworks like Pack-Bayes, or even simpler countable hypothesis bounds with a prior. I think that Bayesian principles are particularly salient in deep learning, where we're using models that can represent many complementary solutions to any given problem, and we really do want to combine these different solutions together, and that can be used in all sorts of exciting downstream applications like Bayesian optimization and active learning. At the same time, there are certain properties of neural nets that do seem to be, of course, relatively distinctive, and I think this includes representation learning, the structure of the geometric properties of the objective functions we use to train these models, and their relative universality. And the latter is something that I'm currently very focused on trying to understand better. All right, maybe I'll just finish with a question. So how many are going to go with the linear function, the cubic polynomial, the 10,000th order polynomial? Okay, very good. All right, thank you.
Any more questions? Maybe I'll ask you an even bigger philosophical question if you like posing them. So, do you believe then, after your talk, that strong AI is possible?
Strong AI meaning?
Meaning that AI can become cognizant and can become like sort of what these fears that people have, that AI will take over the world and these AI machines will rule us, basically. What I mean is like that it can create its own creativity, mind, and so on. I mean, I'm fully with you. I think they're just a tool that fits in our toolkit, and we can analyze them with the same machinery that we have for other things. They're just interesting new mathematical algorithms.
I mean, that's my view of them mostly. I think in principle, it's possible to create intelligences like us, or more effective than us in many cases. I think we are sort of a proof of concept in some sense. I mean, this is something I encountered a little bit when I was debating people about the no free lunch theorems, because quite often people who advocate for the no free lunch theorems as a mechanism for thinking about model construction will say, okay, well, you really want a lot of human intervention, like there always has to be a human in the loop and so on. It's like, but what are we other than like, you know, a program that we could sort of write down algorithmically and automate on a computer? Like, we seem to be sort of like an argument against like the relevance of things like the no free lunch theorems, especially if we're being kind of invoked in the loop in model construction, et cetera. So I think in principle, of course, it's possible. I think we're extremely far away from something like that. It's not something I'm particularly worried about. And I think it's probably more productive to sort of focus our efforts on using machine learning for good, like developing drugs, medical diagnosis, of epidemiology, forecasting, and all sorts of other things. And I think we've seen really exciting progress in these directions.
Since I'm already asking on this high level, so the other question that we started at the very beginning is training.
Mm-hmm.
So I mean, you've now described all these theoretical concepts, but the big problem is still how to train these things efficiently, and that they will, if we were to use them for all these tasks you're asking, will eat up horrendous amounts of energy unless we come up with better ways of training them than stochastic gradient descent. So I'm asking, where should we go on the? I mean, you're advocating the big, large model, which maybe you can convince me that you can train efficiently, but I would still say that training a large, huge model is going to be more costly than training a simple model.
Mm-hmm. So I think a really hard but interesting open question is how we can encode the simplicity bias that we get from scale more explicitly in smaller models. If we think about something like double descent, all of those models are sufficiently flexible to fit the data perfectly. The larger models just have stronger simplicity biases. There are also other procedures like knowledge distillation, where you take a really big model and then you sort of distill it in some sense into a much smaller model that can perform similarly well after that distillation procedure. And so that seems to suggest that the smaller model has some setting of its parameters that can actually approximate the solution that's found by the bigger model fairly well. It just doesn't have the inductive biases to find that solution itself when it's directly trained on the data. And so I think it would be very exciting if we could understand how to encode these kind of simplicity biases in models in a way that's more elegant than just making them bigger. I think philosophically, I do sort of support the idea of scale, but I think it's also possible to scale down very significantly from the models that we're using currently. How to do that, I think, is really a hard problem. Because there are results, some people may have heard of things like the lottery ticket hypothesis and so on, where there's this idea that if you train a really big network, there's some sub-network within that network that would have been able to find the same solution with a particular initialization. The question is, like, do you need to buy lots of lottery tickets to find like the right sort of sub-network? I'm not sure. Mm-hmm.
I'm really interested when you started to do issue models we believe in, and then talked about Bayesian things. So I think one of the conversations we've had is that this subjectivist branch of Bayesian statistics has died out over the past few decades. And how far you'd go with that? Do you believe in your prior distributions? Is it possible to believe in prior distributions there? And so on. So is there a space for this kind of subjectivism?
Yeah, so I'm definitely a subjective Bayesian. I think that we have to sort of try to represent our assumptions as best as we can. And this also involves acknowledging that we're not going to do a perfect job of that. And that might actually start to get a bit controversial with kind of hardline Bayesians. So the thing that I don't like about Bayesian approaches in some cases is this idea that we should pretend that our model is perfectly specified when we know that it's not, that it is misspecified. And so I actually really like things like generalized Bayesian inference, et cetera, where you try to sort of build more robust procedures around what you're doing that will sort of help protect you a little bit more against misspecification by acknowledging that misspecification. At the same time, I think we should still try to do our best in sort of a subjective Bayesian sense to specify our parts. So, like, of course, like, we don't fully believe anything we're doing, but we can try to make what we're doing a closer representation of our beliefs to the extent practical. And sometimes this can be very subtle. So I think a lot of subjective Bayesians will then argue, well, we really want to then sort of push our prior in a direction that's as close to our beliefs as possible. But if that means doing approximate inference, then there's kind of a trade-off. Like if you use something like a conjugate prior that enables exact inference versus a prior that you believe slightly more, that you then have to combine with variational inference or something else, which as a whole is a better encapsulation of your beliefs. So sometimes maybe like choosing the prior that you believe slightly less in the end will ultimately be a better representation of your final beliefs. And so I think this is often very subtle, but I think, modeling things well is very hard and we just can't get away from that. But it makes sense to me to be subjective Bayesian. I think in neural nets, people worry about priors quite a bit. Like, I think this is sort of often a question that comes up, like, well, if you're just putting a generic Gaussian prior over the neural net parameters and then doing marginalization, is that really instilling any meaningful beliefs into what you're doing? I would say it depends on the architecture, but in many cases, yes, because if we were thinking about, like, our beliefs are represented really in function space, not directly in parameter space. And so when we're thinking about distributions over solutions in terms of functions, then a lot of the work that we would do to encode our beliefs would actually go into architecture engineering, like building things like convolutional neural nets that have locality and translation equivariance, et cetera. So if we combine sort of a generic distribution over parameters with those kinds of architectures, then we still induce a distribution over functions that can actually be quite reasonable. And we're still doing something sensible by having that distribution over the parameters, because it's representing our belief that we don't think that the model will be completely specified by the data. And so we do want some sort of uncertainty. And so I think maybe, like, we don't need to worry as much about the details of the distribution over parameters if we're combining it with the functional form of a model that already has all sorts of interesting inductive biases encoded into it. But I guess these, where was it? The benign overfitting results also provide some evidence that maybe these priors aren't so bad after all, because if the marginal likelihood is really going down so much as we do things like increase the number of altered labels, it's saying, okay, well, our distribution of our solutions in the prior isn't happy with that.
Maybe two more questions and
So I have a question about the use of homomorph complexity in the prior. So I mean, I'm a statistician, I don't know. I've come across it being used for analyzing theoretical analysis of algorithms, but how practical is it? Or you just use like literally computation time?
Mm-hmm.
Or
let me see
is
if I can.
Theoretical funds?
Yep. Let's see. Yeah. So this is not being used to intervene on the training of the model at all. So if I were trying to propose a prior over parameters that might induce a prior over hypotheses that was like the Solomonov prior, I think that would be quite computationally intractable. But if instead I've just trained my neural net and then I want to upper bound the Kolmogorov complexity of the solution it finds, this is often something I can do pretty reasonably just by measuring the stored file size of the model. There is some nuance there, though, because if you make the model very big, then there's a question of, like, well, can you actually compress that solution it's found at pretty high fidelity? And there are all sorts of ways you can do that through quantization, for instance, through representing the parameters of the model in a linear subspace. There are some bounds that sort of rely on these compression techniques. There are other bounds that don't, that instead have terms that depend on the spectra of the Hessian and things like this in the solution that you find.
Maybe you can even use, sorry, but just follow up that comment,
Yeah.
it's not a question. Can you use also to choose the architecture, you use total complexity to choose the best architecture in that sense by minimizing the total complexity.
So there's this thing about, like, so it seems that large neural nets have biases for solutions with low Kolmogorov complexity, and that's why using the Solomonov prior in this bound enables us to have fairly tight generalization bounds on performance, and they actually are very surprisingly tight. Like, for example, on CFAR 10, state-of-the-art performance is roughly 95% accuracy. You can bound the worst case accuracy is about 90% using these bounds in expectation.
Yeah, it's also a question.
Yeah, but the other time,
good question.
okay, it's a bit at the end of the talk, you present this work with you put a time series
Mhm.
in a pre-trained LLM and you get
Mhm.
quite good results. So I suppose the idea that with a natural language trained LLM, you have learned, you have been in front of such an amount of training data that you have been able to capture very complex function, and you are able to to forecast an output, because it seems that you have the function inside, you have so many functions that can recognize one input and output. And I wanted to ask you, of course it's difficult to do with ChatGPT, I assume, but what could be interesting and at which point when we change the training data set, okay, at which point we reach universality. So I mean, I imagine that we don't know exactly how many data have been used.
Trillions of
ChatGPT,
tokens,
and
yeah.
exactly, and we cannot do this ourselves, but still it would be interesting, when do we reach this capacity of
Yeah, at what point does it, that's a great question. At what point does it start to become relatively
training?
universal? Most of this paper was trying to understand how these results were possible. And part of the explanation was a simplicity bias. And that becomes quite important in time series forecasting, where quite often you have a very small amount of the potentially available information. So having a very strong Occam's razor bias is going to be quite useful. And that's something we seem to get through pre-training. And that was also partly the explanation for the success of this type of procedure on materials generation. In this case, there are certain symmetries and so on in the solution that we want the model to represent. And it seemed interestingly quite able to discover these rotation invariances automatically. And that's a great way to sort of compress the data. And I actually forgot to mention this slide, but one kind of shocking thing we found in another paper where we proposed a way of measuring learned equivariance across different layers is that vision transformers after training are often more translation equivariant than convolutional neural nets, which is just sounds impossible because conv nets by construction are translation equivariant, but they're not actually fully translation equivariant because they're aliasing artifacts and sort of other issues. And so kind of amazingly, this model that has no explicit bias for translation equivariant ends up finding a solution that's more translation equivariant than even a convolutional neural net.
Yeah, the same kind of results for graph transformers.
Yeah.
So without putting any constraints, we get the network to find good equivariance.
Very interesting. Thank you.
Thank you so much to all of you for the discussion.